Hi, my name is Mahir,
And my name is Rajit.
and we're working on playing Connect 4 with minimax search and alpha beta pruning. So the basic idea of the project is to use minimax search to create bots that will perform well against human players and also against a decent baseline, such as one that makes random moves. Now, the first two heuristics that we implemented for this particular project included two streaks, which is a naive algorithm that just counts up the number of two streaks that a particular board will have and then gives the player a score based on the number of two streaks that it can be generated. And the second one is just a defensive strategy called avoid op4 that prevents the other player from winning. So if you look down here, it blocks the yellow player from getting four in a row by putting a red chip down in front of the fourth piece that it would need.
So our next two algorithms are more sophisticated. They are maximize threats and 2, 3, 4 streaks. So what maximize threats does is two things. First, it tries to get what we call winning rows, where a winning row is a set of four adjacent positions where you have exactly at least one of your color and none of the opponent's colors. So if you look at this red piece over here, this would be a part of this would be a part of the winning row with this piece and the three to the right of it, because you have that piece and yellow has none. So it looks at both your winning rows and the enemy's winning rows. And then it also looks at what we call threats. So a threat is when you have three of the four pieces needed for a connect four, but you don't have one in the last position needed. The other thing that makes something a threat is that you can't currently reach the open position. So this position here would be a threat if this red piece right here didn't exist. So then this would be a threat because you can't currently reach it, but one more piece would finish your connect four. And obviously the enemy's threats are taken into account as well. So in 2, 3, 4 streaks, we're just trying to maximize how many number of 2, 3, and 4 in a row that you have. So for every three in a row that you have, you get some number added to your utility. Whereas if you have two in a row, you get some smaller number added. And then we also give a very large negative utility to boards that are losses in both of these algorithms. So that whenever there's a four in a row for the opponent, that means you get a negative infinite utility. So our two forms of testing for this were testing bots versus bots and a baseline, which was just our random move bot, and testing bots versus humans. Unfortunately, the second part of testing was proved to be difficult to collect just because of the timing of this and finals and willing participants. So ultimately, we were only able to really play against ourselves and gather some idea of what was going on with humans, and mostly use testing bots versus bots. So for our bot versus bot methodology, we need to deal with the fact that all of our heuristics, other than random, were deterministic. So because of this, we would always get the same results unless we introduced some randomness. So how we resolved this was introducing two random moves at the beginning. Then we'd see how each bot would react based on those different starts. So we played each bot against every other bot 30 times and see which bot won more often given these different varying circumstances.
Now, this is the first of two slides on the interpretation of the results that we got. In the table below, what you see in each of the rows is the win, loss, and draw percentage of the red player playing against random. The red player in this case moves first, while random moves second. So as you can see, each heuristic performed extremely well against random. The best heuristics, of course, were the ones that were both defensive and offensive. Those were 2, 3, 4 streaks and maximized threats. Our heuristics did even better against random at higher depth, which makes sense because that allows for more long-term planning and setting up a better position on the board. As a further interpretation of the results, we saw that when algorithms played against themselves, which can be seen here in the black diagonal, the heuristic bot that moved first, in this case given by the red algorithm at the top, actually performed better than the one that moved second. This also makes sense because you can get better positioning if you move first. We also saw that even if you don't look at the diagonal, even in rows that the in which the red first algorithm moved first, it managed to get more wins than the opponent which moved second.
So there are a couple of ways that we could take this in the future to get some improvements. First, just increasing depth. We weren't able to go past depth four when we were running our simulations, just because each move would take about 5 seconds, and therefore it would just take far too long to generate 30 games worth of moves using just bot for spots. The other thing we could do is use machine learning to pick our best features and weights. So out of all the features that we were using for our heuristics, we could assign different weights to those, and then use machine learning to find the optimal weights to get much better performance than we were getting now. Because we were essentially just choosing weights by hand rather than using data to choose our weights for us. So the last thing we want to do is just collect better data playing against humans, because humans might learn strategies more, and some strategies might be weaker against humans than against bots, because of the fact that humans might understand patterns and know how to know how to subvert those patterns as they play against bots more and more. It would be very valuable to look at what happens when we play our bots against humans more, and so we could spot weaknesses in our heuristics that we could shore up. So the basic conclusions of this is that it turns out that minimax search works pretty well for Connect 4. We found that heuristics with that combo offensive and defensive approaches tend to perform better, along with ones that are long-sighted rather than short-sighted. So we also found that the first move, which is red, has a big advantage over yellow. And lastly, that higher depth led to better performance both against our baseline of random and against human players, which is also to be expected since you can see more of the board given a bigger depth. So this is just our table of results that is also available in the paper, but for now we are going to go on to our demo. Okay, so I'll select human versus CPU, and now we've loaded our maximized threat spots into the game. So now, wherever you're gonna notice as I play this game that it's always gonna choose positions that it thinks will have the maximum threats in the future, rather than going for a naive strategy. So the reason it blocked me off here is because it could see into the future that if I got 3 in a row here, then in a couple of turns I'd be able to force a win because I would get 4 in a row in multiple different places. So it had no choice but to block me off there. It needs to block me off somewhere, and it would get more of a threat by going here than it would have by going here. So because of those utilities, it ended up seeing this as the best move. So every move that it's making, it's just evaluating what will give it the highest threat and what will minimize my threat. Hmm. Looks like this one's gonna be a tie.
Block it.
Oh yeah, I had to go
Block
there.
it on 4.
Yeah. Oh, I just lost. Okay. So that was totally not anticipated, but at this point, this heuristic has gotten better than either of the players. So that was our demo.
Yeah. You can see that you have a horizontal.
All right. Thank you.